Hey everybody. Today I want to talk about connective tissue. And connective tissue is the most abundant and widely distributed tissue in the body, even more so than muscle tissue and nervous tissue. It's found throughout the body, but unlike epithelial tissue, it's never exposed to the external environment. So connective tissue is always found within the body. It never has any external exposure like epithelial tissue does. And connective tissue is going to do a bunch of things. It's going to support the body. It's going to surround body parts. It's going to interconnect body parts, interconnect other tissue types. It's connecting the body together. It's going to establish a structural framework for the body. So a lot of different functions of connective tissue. And there are a lot of different connective tissue types that are responsible for performing these functions. And let's just take a quick look at some of these. Bones are a type of connective tissue. They're going to help establish the structural framework for the body. Tendons, which connect skeletal muscle to bone, are a type of connective tissue. Ligaments, which connect different bones together. Down here in the ankle, for instance, there's a lot of different ligaments that connect those ankle bones together. Fat is a connective tissue. Cartilage, which is found many places throughout the body, is a connective tissue. And blood is a liquid connective tissue. So like I said, there are a number of different connective tissue types. And we can divide those into these 4 different categories. And let's just take a look at each of these. The first category is called connective tissue proper. And even within this, there's 2 different categories of connective tissues. There's loose connective tissues and dense connective tissues. Some examples of loose connective tissues are areolar tissue and adipose tissue. Those are 2 loose connective tissues we're going to look at in class. And this tissue right there is areolar tissue. And this tissue down below is adipose tissue. That's areolar tissue. And down below, that's adipose tissue. Then we have the dense connective tissues, still under connective tissue proper. And there's a few of these that we're going to look at in class. There's dense regular connective tissue, dense irregular connective tissue, and also elastic tissue. And this right here is, I'm just going to abbreviate this, dense regular connective tissue, and down below, dense irregular connective tissue. And just comparing the loose and the dense connective tissues, you can kind of tell by their description, that they're a little bit different. These loose connective tissues have a looser arrangement of fibers. They don't look very dense. There's a lot of open space in there. Whereas these dense connective tissues are pretty tightly packed together. The fibers are really packed together in there, and there's not a lot of open space. Another category of connective tissue is cartilage. And there's actually 3 different types of cartilage found different places in the body. There's fibrocartilage, elastic cartilage, and the one we're going to look at most in class, hyaline cartilage. And this tissue right there is hyaline cartilage. Bone tissue is another category of connective tissue, and we're going to look at compact bone. And that right there is compact bone. And then lastly, blood is actually a type of connective tissue. It's a liquid connective tissue. And this is histology of blood. Now, all of these different types of connective tissues are going to have the same three basic components. There's three basic components that are common to all connective tissues. And we're going to go through these, and we're going to use areolar tissue as an example to identify these different components. And one of those components is specialized cells. Each connective tissue has its own type of specialized cell. And the specialized cell that we find in areolar tissue are fibrocytes. Now, there's other types of cells within areolar tissue and within other types of connective tissue, but fibrocyte is going to be the specialized cell type that is special to areolar tissue. Extracellular protein fibers. We're going to find fibers located outside the cells. And there's three different types of fibers that we can find. One are collagen fibers. And collagen fibers are these big, thick, rope-like fibers that provide strength. They have high, what we call tensile strength. They resist stretching. Another type of fiber is an elastic fiber. And these are really thin and they're rubber band-like. And they act like a rubber band. They can both stretch and recoil. And the third type of fiber that we can find are reticular fibers. And reticular fibers are really thin and they form this little network here. And it's a network that capillaries can use for structure, that cells can use for structure, to house themselves on, and stuff like that. And the third component, common to all connective tissue, is a fluid known as ground substance. And all of this empty space in this diagram is ground substance. And as you would guess, ground substance is mostly water. It's a fluid that's mostly water. And loose connective tissues like areolar tissue here is going to have a lot of ground substance. Whereas dense connective tissues like dense regular and dense irregular connective tissue, they're not going to have a whole lot of ground substance in them. And there are pluses and minuses to both of that. If we're talking about the extracellular protein fibers and the ground substance together, collectively we call that the extracellular matrix. And that term makes sense because it's everything outside of the cell. We have the cells like the fibrocytes, and then everything outside of that is the extracellular matrix. And that consists of the protein fibers and the ground substance. And there's some really interesting stuff with extracellular matrix if you want to do some research on this. But I was going to get a bone spur taken off my heel, my calcaneus, and they were going to have to splice a little bit through the Achilles tendon. And to help that heal, they were going to wrap it with extracellular matrix. And apparently extracellular matrix has a penchant for attracting stem cells and stimulating cell growth and helping with repair. And there's another example where veterans of Afghanistan that have stepped on an IUD, for instance, and they get a large part of, let's say, their quadricep muscle taken out. And what they can do is they can take extracellular matrix, they can take tissue from a urinary bladder, and they strip off the cells. And so all that's left is extracellular matrix. And then they put that extracellular matrix down in the damaged muscle tissue. And that's where the magic kind of happens. It attracts stem cells. And it attracts stem cells and it stimulates muscle growth and it helps with muscle repair. So pretty special stuff. Now let's go through and talk about each of these different components, and we'll introduce some connective tissue types in the process. And the first component we'll talk about are specialized cells. So each major class of connective tissue, except blood, has a resident cell type that exists in both immature and mature forms. The immature cells are going to have the suffix blast, and they're responsible for making the extracellular matrix, for producing the protein fibers and ground substance that you're going to find in that tissue. And then the mature cells are going to have the suffix cyte, and they're responsible for maintaining the health of the extracellular matrix. So the specialized cells we're going to find in connective tissue proper, which again includes areolar tissue, adipose tissue, dense regular, and dense irregular connective tissue. The specialized cells we're going to find in these connective tissues are fibroblasts and fibrocytes. And down here we have areolar tissue, and what I'm circling here are the nuclei of different fibrocytes. Okay, the nucleus of a cell stains really easily. And so all of these nuclei are from different fibrocytes. And how do I know they're fibrocytes and not fibroblasts? Well, technically I don't, but if this is mature tissue, if this is mature, healthy tissue, then likely the form that you're going to have there are the cytes, the mature form that are maintaining the health of the matrix. If you have damaged tissue, then that's where the fibroblasts are going to come in and produce more tissue. In cartilage, the specialized cell type we're going to find are chondroblasts and chondrocytes. Chondro means cartilage. And here we have hyaline cartilage. And what I'm circling there are individual chondrocytes. And again, I'm guessing that these are chondrocytes because this is healthy, mature cartilage tissue. If you're making new cartilage, then you're more likely to see the chondroblasts because they're going to be responsible for making the new cartilage. And then in bone tissue, we're going to find osteoblasts and osteocytes. Osteo meaning bone. And this is compact bone we're looking at. These are the structural units called osteons. And within the osteons, you have these rings of extracellular matrix that they call lamella. This is what's called the central canal. That's where the blood vessels and the nerve supply travel through. But these little guys, these little individual black slivers, those are the individual osteocytes. So there's quite a few of them living within that bone tissue there. And again, if this is mature bone, then I'm assuming those are osteocytes. But if you're making bone, if you're during puberty, for instance, or during maybe a fracture and you're repairing bone, then you're going to find the osteoblasts. And I like this figure because it's basically illustrating this point about fibroblasts between blasts and sites. So this is a picture of the skin. It's a figure of the skin. And here's the epithelium, which represents the outer layer of the skin covering the body. That's stratified squamous epithelium. And then underneath that, we have connective tissue. And there's a layer of areolar connective tissue, and then there's dense irregular connective tissue underneath that. But what we're looking at here is we have damage to the skin. We have a puncture wound of the skin, and the skin needs to repair itself. So how is the epithelium going to repair itself? Well, as you guys learned, epithelium is highly regenerative. So there are stem cells located along the bottom layer of the stratified squamous epithelium, and they're going to produce new epithelial cells that are going to replace this damaged epithelium. So that's what the epithelium is going to do. But what about the underlying connective tissue? Well, this areolar tissue and the dense irregular connective tissue that I talked about, those are both connective tissue proper. And so the specialized cell type that we find in both of those are fibroblasts and fibrocytes. And so here they show fibroblasts. And what are these fibroblasts doing? Well, they're secreting extracellular protein fibers. They're secreting ground substance. They're essentially making new connective tissue, making new areolar tissue, and making new dense irregular connective tissue. Now let's move on to the extracellular protein fibers. And the first protein fiber I want to talk about are collagen fibers. And collagen fibers are constructed primarily of the fibrous protein collagen. And the deal with these collagen fibers is they're extremely tough. And they provide very high tensile strength to the tissues they're in. Tensile strength is resistance to stretching. And so they're really strong and they resist stretching. They have a high resistance to stretching. And over here in the areolar tissue, these big, thick, pink bands, these are collagen fibers. And so there are some collagen fibers in areolar tissue. But if you want to find a lot of collagen fibers, then you can look over here to dense regular connective tissue. And dense regular connective tissue is composed primarily of collagen fibers. These are all collagen fibers waving down through this tissue. It's almost like you stuck your fingers in red paint and you just ran them down a sheet of paper. So all of this red material represents collagen fibers. Those are collagen fibers. And that's why it's considered a dense connective tissue, because it's densely packed with these collagen fibers. Now, where are we going to find dense regular connective tissue with all of these collagen fibers? And by the way, all of these collagen fibers are running in one direction. Okay. Well, one place we're going to find those is in the tendons. Tendons are made up of dense regular connective tissue. So what do tendons do? Well, tendons attach muscle to bone. And here, this right here is the, what tendon is that? That's the Achilles tendon. And the Achilles tendon attaches muscle. It attaches the calf muscles, the gastrocnemius muscles, to bone, to the heel, to the calcaneus. And what happens is when skeletal muscles contract, when they shorten, they pull on the tendon pulls on the bone, and the bone moves. And thereby we produce movement. So the skeletal muscle contracts, that tension gets applied to the tendon, and the tendon pulls on the bone, and the bone moves. Your heel moves up in this case. So a question I want to ask you is, how is this an example of the complementarity of structure and function? How does the structure of dense regular connective tissue complement or determine the function of the tendon? How is this an example of complementarity of structure and function? Well, to answer that, first of all, you need to know that you don't want tendons to stretch. Okay, when you stretch a tendon, that's not a good thing. You want them to transfer the entire pulling force of this muscle down to this bone. So you want this tendon to resist stretching. And these dense collagen fibers are going to resist stretch. So that's one example of the complementarity of structure and function. Tendons resist stretch, and they do so because they're made of collagen fibers. But furthermore, all of these collagen fibers are running in one direction, which means they're going to resist stretch in one direction. And tendons are only pulled in one direction. And so that's another example of this complementarity, that you have dense collagen fibers running in one direction, and that means that in tendons, they're going to resist stretch when they're pulled in one direction. We also find an abundance of collagen fibers in dense irregular connective tissue. And this is dense irregular connective tissue. And all of these big, thick bands are all bands of collagen. But what's different about dense regular connective tissue and what we're seeing here, dense irregular connective tissue? What's different about those collagen fibers? Well, in dense regular connective tissue, all of the collagen fibers ran in one direction. But in dense irregular connective tissue, you have collagen fibers that are running multiple directions. And what that means is it can resist stretch in multiple directions. It just doesn't resist stretch in one direction, it resists stretch in multiple directions. And so where are we going to find this? Because of this, you're going to find dense irregular connective tissue in structures where tension is exerted in many directions. And joint capsules are a great example of this. Here we have the hip joint. This is the head of the femur that fits in this socket, the acetabulum on the hip bone. And this is a synovial joint, which is surrounded by a joint capsule. And guess what? When you move this leg, this is a ball and socket joint, which means you can move this leg in multiple different directions. There's a lot of different motion you can have at this hip joint. And because of that, this joint capsule is going to be pulled in many different directions. And again, we don't want this joint capsule to stretch. We want it to maintain its integrity. And so dense irregular connective tissue is a great tissue to make it out of because it's going to resist stretch in multiple directions. Another type of extracellular protein fiber are elastic fibers. And elastic fibers are long, thin fibers that contain elastin. And this is a rubber-like protein. And what that allows these elastic fibers to do is it allows them to not only stretch, but it allows them to recoil. Okay, they act like a rubber band. You can stretch a rubber band, but it will also recoil on itself. And those are two important properties to have. So where are you going to find elastic fibers? Well, there are elastic fibers in areolar tissue and other tissues, but one place you're going to find a large number of elastic fibers is in elastic tissue. And all of these thin, dark fibers in there are individual elastic fibers that all have rubber band-like properties. So where are you going to find elastic tissue? Where are these elastic fibers really going to have a benefit? Well, you're going to find elastic tissue in the major blood vessels that exit the heart, including the aorta. And why would you want the aorta made out of elastic tissue? We'll look at this diagram down here. So this represents the heart, and this represents the aorta. And what's going to happen when the heart contracts, when the ventricles contract? When the ventricles contract, they're going to shoot a large amount of blood out into the aorta. And the elastic fibers that make up the aorta are going to allow the aorta to expand and to absorb that pressure. So you have this huge influx. You have this huge influx of blood into the aorta during ventricular contraction, and that elastic tissue allows the aorta to expand. Just as importantly, when the ventricles relax and they stop shooting blood out through the aorta, this elastic tissue is going to allow the aorta to recoil. And by doing so, by recoiling, it maintains pressure on the blood that's in there. Okay, it recoils and it maintains blood pressure. And so this elastic tissue is important because it allows for continuous blood pressure in the blood vessels. During ventricular contraction, it's going to stretch and the blood pressure is high during that time. And then during ventricular relaxation, the aorta is going to recoil and maintain the pressure on that blood. And so you're going to maintain blood pressure and therefore maintain blood flow. People with heart disease, atherosclerosis, for instance. Atherosclerosis is the hardening of the arteries. And that means that the arteries are unable to expand and recoil. So what happens is that when the ventricles contract and they shoot a bunch of blood out into the aorta can't expand. And that means you get this super high spike in blood pressure. And then when the heart relaxes, the aorta is not able to recoil. And so the blood pressure goes way down. And so instead of having these kind of normal pulsations in blood pressure, systole and diastole, you have these huge pressure swings during ventricular contraction and ventricular relaxation. And your blood pressure is inconsistent as a result of that. And the last type of fiber are reticular fibers. And reticular fibers are short, fine, collagenous fibers. And they're going to branch extensively, and they're going to form delicate networks that are going to surround and provide support for cells in small blood vessels, like capillaries. So they form this network of fibers like we see here, and that's going to provide structure, it's going to provide support for capillaries that may pass through there. It's going to provide support for cells that live in that tissue. And a good place to find reticular fibers is in reticular tissue. This is reticular tissue that we find in the spleen. And you can see these small, fine, delicate networks. And when we get to the lymphatic system, we'll talk about this, but the spleen is a lymphoid organ. And the spleen provides structure, it provides housing for the immune system, which means that there are millions and millions of white blood cells that live within the spleen. And they're going to live on these little reticular fibers that are found in the spleen. And the same is true for lymph nodes. Lymph nodes have these networks of reticular fibers in them. And lymph nodes, like the spleen, have white blood cells that live in them. And you can see these white blood cells, lymphocytes, macrophages, they're basically just hanging out. They're living on these reticular fibers, waiting for pathogens to pass through the lymph nodes so they can attack them and alert the immune system. So this is a good example of what reticular fibers do. They provide a fine, delicate network where cells and other structures like blood vessels can provide support for them, can provide structure for them. And the last component, common to all connective tissues, is ground substance. And ground substance is the unstructured material that fills the space between the cells and the extracellular protein fibers. So down here, both in this areolar tissue drawing and the areolar tissue histology, all of this empty space in here, both in the drawing and in the actual histology, all of this empty space represents ground substance. And this ground substance is mostly fluid. It's mostly water. And so one of its functions is it's going to function as a medium through which nutrients and other substances can diffuse from the capillaries to the cells in those tissues, and vice versa. So for instance, here we have blood vessels. And here we have a fibrocyte. And this fibrocyte needs oxygen. It needs glucose. And how is it going to get it? How is it going to get it? Well, both of those things, glucose and oxygen, are going to move from the capillaries into the tissue, and this ground substance is going to provide a medium that those substances diffuse through to reach the fibrocyte. On that same note, this fibrocyte is producing carbon dioxide and other metabolic waste products. And those waste products are going to diffuse through this ground substance, through this fluid, until they reach the blood vessel. And then the blood supply can take them away. Tissues with large amounts of ground substance, like areolar tissue, have lots of space for blood vessels. So with all of this ground substance, that provides a lot of space for blood vessels to penetrate. And so tissues with large amounts of ground substance are well vascularized. They have a rich blood supply. Now, because of these properties, because areolar tissue has a large amount of ground substance and is well vascularized, areolar tissue is going to be a great support tissue. And specifically, it's going to be a great support tissue for the epithelium of the body. So we're going to find areolar tissue under all of the epithelial sheets that I know of is going to have a layer of areolar tissue underneath it, directly underneath it. It's going to be a great support tissue for epithelium. And why is that the case? Here we're looking at the skin, and here's the stratified squamous epithelium that makes up the skin. And then underneath that, we have a layer of areolar tissue. Now, why is it beneficial to have areolar tissue underneath this epithelium? Well, it's beneficial because epithelium is avascular. It doesn't have a direct blood supply. And so it needs to get its nutrients and its gases from the underlying connective tissue. And because areolar tissue is well vascularized, it's a great support tissue for that reason. So oxygen and glucose and other beneficial things are going to be able to diffuse from the blood vessels in the areolar tissue through that ground substance and provide these epithelial cells with what they need. And at the same time, those epithelial cells are going to give us waste products, and those waste products are going to diffuse through the ground substance of the areolar tissue and be taken away from the blood vessels in the areolar tissue. So it's a great support tissue. Another benefit of having all of this ground substance is that it provides a lot of space for the presence of white blood cells. And so typically where we have areolar tissue, we're going to have a lot of white blood cells patrolling the area. And that's what's represented in this figure. All of these different types of immune cells. And that's good because, this epithelium is exposed. And so pathogens can, potentially come in. And if they want to get into the blood supply, they have to do so in the areolar tissue. And so it's nice to have areolar tissue there because you're going to have a lot of white blood cells that are present, and they can come and attack any potential pathogens. The areolar tissue that is in the digestive tract, that's underneath the epithelium lining the digestive tract, has millions of white blood cells in it. In fact, there's more white blood cells in the areolar tissue underneath the epithelium in the digestive tract than anywhere else in the body. So we're talking about areolar tissue here and how well vascularized it is. And that just reminded me of a point I wanted to make in an earlier slide. This slide here. And so here we're back to dense regular connective tissue. And, is there a lot of ground substance in dense regular connective tissue? And the answer is no. So what does that imply about the blood supply there? Is dense regular connective tissue well vascularized? It's not. Dense regular connective tissue has a poor blood supply. There's just not any extra space in here for blood vessels to penetrate. So what does that mean? What if you have damage? What if you strain or you tear your Achilles tendon or any other tendon in your body? Is that going to be a quick healing process? It's not, because it does not have a good blood supply. So it's not going to give it the support that it needs to heal quickly. So tendons and ligaments and joint capsules and stuff like that, they're going to take a while to heal because they have a poor blood supply. And that's because they do not have a lot of ground substance. There's just not a lot of space for blood vessels to penetrate. All right, so next I just want to talk about a few other connective tissues that we haven't talked about yet. And one of those is adipose tissue. And this is the histology of adipose tissue. And what does it look like? Kind of looks like a lot of bubbles. Looks like it's a bubble bath, or it has a chicken wire appearance to it. So it's pretty distinct like that. And within adipose tissue, the primary cell type you're going to have are adipocytes. And each one of these is an individual adipocyte. And what do we find within adipocytes? What do they do? Well, adipocytes store fat. They store triglycerides. Okay, so these are the function. One of the functions here is energy storage. And triglycerides don't stain, which is why the inside of these cells don't stain. And something that's interesting is these cells can get so filled with triglycerides that it pushes the nucleus to the outside of the cell. So the nucleus isn't in the center of the cell, but instead it gets pushed to the outside of the cell. So this is adipose tissue, and adipose tissue is found throughout the body. It's not only energy storage, but it's thermal insulation, and it also serves as a shock absorber. And then we have cartilage, and specifically we're looking at hyaline cartilage. But what all cartilages have in common is they're made up primarily of water. They're made up of up to 80% water, which is important when we talk about the function of cartilage. Here are the specialized cells that we find in cartilage, chondrocytes. And these chondrocytes live in these chambers called lacunae. So each chondrocyte has its own little house, its own little lacuna that it lives in. Now there are fibers in hyaline cartilage. In fact, there's large numbers of collagen fibers there, but you just can't see them in the extracellular matrix. For some reason, maybe it's because there's so much water in there, I'm not sure. But you can't see the collagen fibers there. And so what you're left with is this kind of glassy appearance to the hyaline cartilage. So cartilage is found lots of different places throughout the body, but one of the places we find hyaline cartilage is on the ends of long bones. So we can imagine that this is the knee joint, which would mean this is the femur, this is the tibia, and each of those bones, each of those long bones, has a pad of hyaline cartilage on it, on the ends of it. And this is all contained within the knee joint by this joint capsule. And as we'll learn later when we get into the skeletal system, there's synovial fluid in here as well. But what's the benefit of having pads of hyaline cartilage on the ends of these long bones? Well, you can imagine that if you're running or you're hiking, then there's going to be a lot of compression occurring at the knee joint. And these two bones are going to want to bang together. They're going to want to hit each other. And this cartilage, because it's made up of 80% water, is going to absorb a lot of that shock. And not only is it going to absorb that shock, but when the compression ends, that water is going to allow the cartilage to rebound and to go back to its normal shape. So they're shock absorbers. Because you certainly don't want bone hitting bone there. And over time, as your cartilage wears out, that can happen. Then we have bone. And we're looking at compact bone in this figure, in this histology. And again, we're going to go over this in more detail when we get to the skeletal system, but I can at least introduce it here. So the specialized cells that we find in bone are osteocytes. And these little black slivers are individual osteocytes. And like the chondrocytes in cartilage, these osteocytes are going to live in individual lacunae. You just can't see those chambers necessarily in this diagram. So those are the specialized cells. What about the extracellular matrix? What's the extracellular matrix made up of? Well, the extracellular matrix is, as you know, it's hard. And it is that way because it's made up of a lot of calcium and phosphate. So that makes up the extracellular matrix. We're also going to find collagen fibers in the extracellular matrix as well. And lastly, we have blood. And blood is a liquid connective tissue. And the specific cells we're going to find in there are red blood cells and white blood cells. And the extracellular matrix is a fluid matrix. And we call this fluid within blood, we call that plasma. And plasma, like other fluids in the body, is mostly water.